Encore. Je sais pas si vidéo, c'est pas HDMI. HDMI 1. Essaye avec le celui-là. Ah, mais parce qu'il faut le. Non, il va mettre. Okay, because mine not working. Okay.
Good. No, sur Zoom ou pas?
Sur Zoom, c'est quoi le problème? Il faut arrêter le partage et remettre le partage. C'est bon? C'est checké?
Okay.
So now we have Enrico, who's going to talk about eccentric disks with phantom. So the floor is yours. I will let you know in 3 minutes.
Okay, thank you. So, hi everyone, thanks for organizing this very nice workshop here. So today I'm telling you about eccentric disks with phantom. So it will be a bit like a, yes, I put together this presentation. I'm not sure whether it will be completely effective, but please feel free to interrupt me whenever you feel that you're not understanding, and try to figure out whether I can explain things better. So first thing, so what are eccentric disks? So eccentric disks are actually nothing different from more general types of circular disks, basically. So we need to always remember that accretion disks are actually a very special class of eccentric disks with zero eccentricity. So you need to think about eccentric disks as a set of nested ellipses, confocal ellipses with an eccentricity profile, and also with a longitude of pericenter profile. So just to make sure that we are all on the same page about concerning like the quantities here. So the ellipses like has a semi-major axis that is like the half major axis of the ellipse. The focus is like at the distance from the center of the ellipse of A times E cav, like 8 times the eccentricity of the disk. And you do not need necessarily to have a cavity. So in this case, the cavity is eccentric. It's just like an example of a situation where the disk is eccentric. So, and also another important quantity is like are the angles in this problem, which and one should never like confuse true anomaly with eccentric anomaly. So throughout this presentation, we will always use the true anomaly, which is calculated from the focus of the ellipse. And in general, like our reference system will be centered in the focus of the ellipses. So why is all this interesting? The thing is that there are like plenty of situations in astrophysical environments where you get eccentric disks. One of the examples was, for example, Josh that was just discussing. And the thing is that so far we are not like, we have not spent enough efforts in trying to model these disks properly and in a consistent way, like with proper equations. So these are some examples where these things are, where eccentric disks are relevant, and but also like beyond situations that we have discussed a lot of concerning protoplanetary systems. There are also some situations with like higher energies that for which this is relevant. So, but most interestingly, actually, one of the things that we usually forget to discuss is that with ALMA now we have like, and we have a sensitivity to, not sure whether sensitivity is the right word, but the kinematics, actually we can measure velocities down to 50 meters per second, which is like a fast car on the Autobahn in Germany. And how this translates in the amount of like the amount of eccentricity that we can actually measure, and it's quite impressive because I mean, if you do the numbers, basically at 50 AU, so this plot is showing you like with using these equations, the minimum eccentricity that you can measure at the distance from the central SAR, from the center of the system, like of like in the I mean, most it depends obviously on the inclination of your system, but it goes down like to below 1%. So like the type of measurements that you can actually do is like insane with ALMA, but still we are not ever modeling this properly. So this brings me to explain, like, because I did my homework before coming here, and basically I pushed like a branch of my fork where I had started like working on a few years ago, actually, working on developing a setup for initializing eccentric disks with Phantom. And so today I'm giving you like a brief tutorial about how I did it, and like how you can do it yourself, actually. So, I mean, it started like with a master thesis project that ended up being probably too complex for a master student. Because in fact, like if you look at this, like the papers that describe the dynamics of eccentric disks actually is like are like an insane amount of equations with contravariant notation. And also, like, this is my most theoretical collaborator that actually picked it. I asked him, pick an equation that is particularly complex, and you can find that they even redefined like partial derivatives with these weird things. So just to say that it is like a very complex problem. But so again, but 7 years later, I mean, after like starting this project with this master student, so we ended up in Ragusa et al. 2024 providing like a more concise and more accessible discussion of eccentric disk dynamics. It's not that it's still like the same formalism used there. Like it's like we just simply changed the language to make it a bit more accessible and like making it like more usable in daily life, let's say. So the most important thing that one needs to understand about eccentric disks that makes them particularly complex is that it's not just the azimuthal motion that changes, but the fact that you have like that the material actually changes the geometry of its orbit throughout along its path. You also start having like vertical oscillations. So the eccentric disks are actually breathing between pericenter and apocenter. And so you can actually detect also like vertical velocity signatures in these systems. So why this is complicated, actually? So why initializing this disk was particularly complex? And the reason is that like along the orbit, the material actually changes, as I said, the geometry. And basically, after like a few simple passages, which are definitely not, I mean, it's not that complex, but it's relatively easy. You find that there is like a quantity that is conserved along the orbit, which is the flux. But the expression of this flux actually depends on the Jacobian, which, as I've not emphasized, this is this beast here. So when you want to initialize an eccentric disk, actually, you need to account for both the distribution of mass in the disk, radial distribution, which actually is a function of the same major axis, but also about it's a function of the azimuthal quantity, so of the true anomaly. So this like is a snapshot telling you what I mean. So as soon as you have like the disk starts twisting, or you have a profile of the eccentricity, orbits start clustering, producing an overdensity. So you need to account for this when you are like initializing your disk. And that was definitely not straightforward, because the thing is, if you start your disk without accounting for this, you will not conserve the flux of the material along the orbit, and this will end up like creating a sort of huge mess in your setup as soon as you start your simulation. So this is an example of like different profiles. Like these are like weird profiles, obviously, but showing you like how the density changes, like azimuthally, depending on how steep is the gradient of the eccentricity. And so in general, like how do we implement this in Phantom? So how we end up doing this, accounting for this azimuthal dependence. And the way we do this in the end is like we use a trick, because instead of using like this complicated quantity that describes the azimuthal dependence of the disk density on the azimuth, we actually perform like during the you know that particles in phantom are distributed in the disk using an accept reject method. So we instead we generate this time like a triple of A, which is the major axis, phi, and which is the true anomaly, and F, which is like a uniform random variable that allows you to accept or reject. But then what we do is, instead of sampling like phi with this weird distribution that comes from that complicated quantity that I was discussing, that is the Jacobian, we actually use the mean anomaly, which is like another quantity, another angle that is used mainly for allowing you to pass from, so it's a quantity that is used a lot in celestial mechanics, that basically tells you, allows you to pass from an angle that is defined like as evolving in time, like with a linear evolution. Like it's like if your mass, along the orbit, your companion is actually moving with a uniform motion, so not accounting for speed up at pericenter and apocenter. But in any case, like there is like an equation that allows you, that there are like equations that allow you to move from this quantity that can be sampled uniformly to the true anomaly. And this actually gives you the right distribution along the orbit, as I was showing you in the plots before. So the velocities I'm using in this context actually are like the Keplerian velocities. I'm not changing, I'm not applying any correction for pressure. So this is the setup that is at the moment implemented like in Phantom. So, but actually, because pressure effects are complicated to account for, because it depends a lot on on the type of prescription that you're using for your pressure effects. So how you use this? So you basically make a phantom setup file. You then run the phantom setup, and now you will be asked for first to initialize your disk using a sigma profile that is tabulated in a file. So this is also something that you can use in general, like without the need to use the eccentric disk. This is a new feature that you can use. And then you will be asked to start whether you want the disk to be eccentric. And this will actually allow you to choose between multiple options about how to initialize your disk. The best option that I see is tabulating also your eccentricity profile. So I've also included like a small script that creates the right files, the right tabulated files that you need to start your setup. You need just to change in this script like the profiles that you want, and this will generate the right files for you. And then so this is an example. I use like a constant eccentricity profile here in this case, and this profile for sigma. The important thing that you need to keep in mind when you're using this tool actually is that you need to keep, so the script automatically rescales the radii that you're using, the innermost radius and the outermost radius, with the radii that you have imposed in your setup file. But you need to be careful about maintaining the ratio between the inner radius and the outer radius to be the same. Otherwise, you are stretching your profile. So this is what you get if you initialize the setup this way. I'm showing you also, like I also included some scripts to extract from the dumps actually the eccentricity profile and the sigma profile as a function of the same major axis, which is very important because you see here, for example, if you're plotting in an eccentric disk, a significant eccentric disk, the sigma as a function of r, instead of as a function of the same major axis, you get a bit of a mess because you are spanning orbits that are not multiple orbits, basically. And finally, this is a small video showing, like, this is a numerical simulation with the binary, starting already with an eccentric disk. So you might wonder, like, why I did all of this just for the sake of this. But so there are multiple projects that I have ongoing on this. So one is like, sorry, I just wanted to tell you, I forgot. Maybe I'm going too long. I just wrap up. Yeah,
30 seconds.
30 seconds. Yeah. Okay. The main thing that I want to say then, so let's skip to the conclusions. Because here is. So the main thing that I wanted to tell you about this is, don't expect to initialize your profiles and to have them like evolving as you would expect. So eccentric disks are bad beasts in the sense that they are well behaved only in situations when you have the right eccentricity profile and sigma. And the reason for this is that the pressure by itself produces like a precession that is differential to the disk. So as soon as you start the simulation without having the right eccentricity profile, your disk will start twisting, producing this type of ellipses that you see. Sorry, this type of spiral features that you see here. So this is pretty much all I wanted to tell you. And sorry for being a bit long. And